Welcome, students. Today we're going to begin our unit on polynomial functions, which will last about 2 weeks. And right now we're going to look at the definition of a polynomial function, an example, and some graphs of basic polynomial functions. So a polynomial function is just a function whose equation is in the form of a polynomial. So for example, we could have f of x equals x to the fifth minus 5x cubed plus 4x. We're going to be looking at polynomial functions like this, and we're going to be building up to seeing what their graphs look like. But for now, I want to just remind ourselves of some of the vocabulary that we have regarding polynomials. Remember that the degree of a polynomial is the exponent on the term that has the highest exponent on the variable. So in this case, the degree of the polynomial is 5. It is a 5th degree polynomial. We can also talk about the coefficients. The coefficients are the numerical factors in each term. The coefficient here is 1, even though it's not written. X to the 5th is the same as 1 times x to the 5th. The coefficient here is negative 5. And the coefficient on this term is 4. We also have the leading coefficient. Remember, the leading term is the term that has the highest degree. And in this case, that's x to the 5th, and the leading coefficient is its coefficient, which is 1. It's important to have a basic understanding of these vocabulary terms because we're going to be using them later. For example, the graph is going to look different if the leading coefficient is positive versus if the leading coefficient is negative. We spent a lot of time looking at second-degree polynomial functions whose graphs are parabolas. We're going to be looking at higher-degree polynomial functions and their graphs, and we're going to see that these are in general more complicated, but we're going to start with something that is simpler. We're going to start by looking at the graphs of polynomial functions that are monomials. So let's consider p of x equals x to the n. We've already seen the graph of x squared, and we've seen the graph of x cubed. I want to look at those again alongside the graphs of x to the 4th and x to the 5th. And here we have the graphs of y equals x squared, y equals x cubed, y equals x to the 4th, and y equals x to the 5th. I want to talk about similarities and differences here. One similarity is that all of these graphs contain the origin as a point, and another similarity is all of them contain the point 1, 1. This is because 1 squared is 1, 1 cubed is 1, 1 to the 4th is 1, and 1 to the 5th is 1. But one thing that's different is that some of the graphs are going up to the right and to the left from the origin, and others are going up to the right and down to the left from the origin. The reason for this is when we take a negative number and raise it to an odd power, the result is negative. So when we've got a negative x value here, we're going to have negative y values whenever the exponent is odd. So for the x squared and x 4th and the other even powers, we contain the point negative 1, 1. But for the odd powers, we contain the point negative 1, negative 1. All right. Another difference is how quickly these graphs are increasing. If we look to the right-hand sides of these, after the point 1, 1, we end up having graphs that get steeper and steeper and steeper. This is because as the exponent grows, the values of the function are generally growing much more quickly. 2 to the 5th is much bigger than 2 to the 4th, which is bigger than 2 to the 3rd, etc. However, when we look close to the origin for all of these, as the exponent gets bigger, it actually gets flatter. You can see that the function values are smaller when we're close to 0, the higher up the exponent goes. That's because when you take a fraction that's less than 1, like 1/2, and you raise it to a large exponent, it's getting smaller and smaller much more quickly. So these graphs have a lot in common, but as the exponent increases, they get flatter close to the origin and then steeper when we're outside of the domain from -1 to 1. Now, knowing a lot about these graphs is useful because sometimes we can use these basic graphs and transformations of functions to sketch new graphs. Let's sketch a graph of g of x equals -2x to the 5th plus 4. Now, we're going to need an xy plane for this, so here we go. Oftentimes, when we're dealing with polynomials, our graphs are going to grow more quickly than when we were dealing with linear functions, and so I will often use a vertically oriented xy plane template. It just works out better generally when we're dealing with polynomials. So what we want to do here is we want to look and see how we can get this function as a series of transformations from the function f of x equals x to the 5th. So we need to go from x to the 5th to -2x to the 5th plus 4. The first thing we can do is replace x to the 5th with 2x to the 5th. And when we replace a function with 2 times its function, this gives us a vertical stretch by a factor of 2. Then we can replace the function with its opposite, and what that does is it gives us a reflection. We reflect about the x-axis. It's a vertical reflection. And then finally, we can replace our function with our function plus 4, which gives us a shift up by 4 units. And now we have our function g of x equals -2x to the 5th plus 4. So what we're going to do is we're going to take the 3 points that we know we have on y equals x to the 5th, and we're going to plot them and then put them through all of these transformations. I'm not going to pick any more points because if we said x equals 2 and we wanted to know the point that corresponded there, 2 to the 5th is 32, which is well outside the range on this template. So I'm just going to use these 3 points. The upside is that this shouldn't be too difficult to get a generic idea of what our graph is going to look like. But the downside is that it's not going to be very accurate outside of in between these 3 points. So right now, our goal isn't to get the most accurate graph in the world. Our goal is to just get an idea of what this graph is going to look like. So let's start by plotting the 3 points that we know are on the original graph, 0, 0, 1, 1, and -1, -1. And let's put these points through the series of transformations we have here. First, we have a vertical stretch by 2. So these points end up being twice as far from the x-axis as they started. Of course, the origin won't move at all. Then we need to reflect about the x-axis. We've got a vertical reflection. So the points that are above the x-axis get reflected so that they're below the x-axis. And then the points that are below the x-axis get reflected so that they're above the x-axis. And again, the origin will not move for a reflection. And then finally, we need to shift each of these points up 4 units. So if each of these points goes up 4 units, that's going to give us -1, 6. It's going to give us 0, 4, and it's going to give us 1, 2. Now we need to connect these dots to get our graph, and what I want to point out is that x to the 5th goes up as we move from left to the right, but because we've reflected about the x-axis, we're going to be going down as we go from left to right. So our graph is going to look something like this. And this is g of x equals negative 2x to the 5th plus 4. Again, it's not a super accurate graph because we only have 3 points, but it does give us a bit of an idea of what it's going to look like. In the next video, we're going to look at more general examples of polynomial functions and their graphs, and we're going to start the kind of long process of learning more about polynomial functions and how to graph them accurately.